Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this. When you think about space travel, what's the first image that comes to mind?
For most people, I bet it's that classic rocket launch.
Exactly. Fire, smoke, this enormous vehicle just fighting its way off the planet. Maybe, a Soyuz lifting off from Baikonur.
It's an incredible sight, no doubt. Powerful.
Definitely powerful. But that image, that very picture of a rocket launch, it actually highlights this huge fundamental problem, a challenge that's really held back our bigger dreams for exploring deep space for, over a century now.
It really has, because despite all our advanced engineering, rockets still work on a pretty simple principle.
Newton's third law, right?
That's the one. For every action, there's an equal and opposite reaction. You burn fuel, throw that mass backwards really fast.
And the reaction pushes the rocket forwards. Simple physics.
Simple, but brutal. And inescapable, really.
And needing to throw mass away like that leads straight to the big mathematical hurdle. The one Konstantin Tsiolkovsky figured out way back in 1903.
Ah, yes, the famous rocket equation.
It basically spells out this limit, the mass ratio problem, and people call it a tyranny for a reason.
It absolutely is a tyranny. It traps us in this vicious cycle.
Yeah.
See, the fuel you need to speed up your spacecraft, it's heavy, really heavy.
And you have to carry that fuel on the rocket.
Which means you need more fuel just to lift the first batch of fuel. It gets exponential.
Right. Tsiolkovsky's equation just lays it bare. That desired speed change, engineers call it delta V. It depends exponentially on how much of your rocket is fuel versus payload.
And exponential here is, it's punishing.
Maybe give us a sense of that. Like if you want to double your speed leaving Earth orbit.
Yeah, good point. Doubling your speed might mean you need, say, 5 times the fuel, not just twice as much, maybe even more.
Wow.
And for really ambitious stuff, deep space or, a big dream interstellar travel, you need huge delta V.
So the amount of fuel you need just skyrockets.
Exactly. The mass fraction, the percentage of your rocket that's just propelling it gets closer and closer to 100%.
Like 99% fuel, 1% spaceship.
Or even 99.99% fuel. You're basically launching fuel to launch fuel to launch fuel. It makes high-speed interstellar travel seem, not just hard, but almost physically impossible with chemical rockets. We just can't carry enough energy that way.
Okay, so that sets up our mission for this deep dive then. The sources you've looked at, they're all about breaking that cycle, aren't they?
Precisely. The big question driving this is, what if spacecraft didn't have to carry their propellant? What if they could just leave the fuel behind?
Find another way.
And that's exactly what's explored in this really comprehensive new review. It popped up on the ArXiv preprint server by Romania Kezarashvili.
ArXiv, right, the physics preprint place.
Yeah. And this review looks carefully at different ways to get propellantless propulsion. So systems that don't burn onboard mass, but instead tap into forces and energy that are already out there in space.
We're not just talking about making rockets a bit more efficient.
No, not at all. This is a whole different way of thinking, a paradigm shift, really.
So the big takeaway right up front.
The crucial point from the review is that these propellantless methods, they aren't just improvements. They could actually enable missions that are completely impossible right now with conventional rockets.
Especially if you want to go far, like really far, beyond Pluto kind of far.
Exactly. Getting rid of that need for propellant, escaping the mass trap, it changes everything. Mission design, what's feasible, the whole game.
Right, so where do we start? There's one method that's actually been used for quite a while, hasn't it? Less future tech, more clever maneuvering.
That's right. The gravity assist. It's probably the simplest propellantless technique, and it's got a proven track record going back decades. We could call it maybe the easiest theft.
Huh. I like that. A theft of momentum.
Conceptually, yeah, that's pretty much it. It's elegant, really. You time a spacecraft's flight path very, very carefully so it swings close by a big planet like Jupiter or Venus.
You fly past it on a specific path, a hyperbolic trajectory, I think it's called.
Correct. And as it swings by, the spacecraft and the planet exchange a bit of momentum. The planet has so much momentum it barely notices.
But for the tiny spacecraft.
For the spacecraft, it's huge. It effectively steals a tiny fraction of the planet's orbital momentum, and that translates into a significant speed boost for the probe. Completely free. In terms of fuel,
It's like a cosmic slingshot. Conservation of energy doing the work.
Exactly. And the textbook example, the one everyone points to, has to be the Voyager probes.
Ah, Voyager 1 and 2. The Grand Tour.
The Grand Tour, yeah. Launched back in the late 70s, they took advantage of this really rare alignment of the outer planets.
Jupiter, Saturn, Uranus, Neptune.
Mm-hmm.
They visited all four, didn't they?
They did, using one gravity assist after another to hop from planet to planet, getting boosts along the way.
And doing that with chemical rockets alone, carrying enough fuel.
Impossible. Just completely impossible. The amount of fuel needed would have been astronomical. Voyager is just this stunning example of how powerful orbital mechanics can be.
It really is brilliant, a testament to clever engineering and physics. But there's always a but, isn't there? The review mentions the trade-offs.
There are always trade-offs. Gravity assists work, we've mastered the technique, but they have some pretty big practical limitations.
You can't just decide to do one whenever you feel like it.
No, absolutely not. That's the main constraint. You are completely dependent on the planets being in the right place at the right time.
Relative to each other and relative to where you want to go.
Exactly. These alignments are rare. The Voyager opportunity, for instance, only comes around once every 176 years.
Wow. So mission planners aren't just looking at next Tuesday. They're looking decades ahead, mapping planetary positions.
They use these things called pork chop plots.
Pork chop plots.
Seriously, they're graphs that show the possible launch windows, flight times, and energy needed. They basically highlight how you only get these narrow windows, maybe a few weeks every few years or even decades, to launch if you want to use a specific gravity assist path.
So very limited opportunities, and the path itself.
It's totally inflexible once you launch. You're locked into that trajectory. It's dictated by celestial mechanics, by the cosmic clock, not by where you might want to go explore next week.
So, great for pre-planned tours, but not for flexible, on-demand exploration. If you need continuous thrust or the ability to change course easily.
You need something else. You need to look beyond planets and start tapping into the energy sources that are always there in space.
Okay, which takes us to the next step. Moving away from these occasional gravitational boosts towards something more constant. Yeah. And this is where, I think you said it gets really interesting, harnessing sunlight itself.
Exactly. Solar sails. This shifts the concept from borrowing momentum from a planet to catching momentum from the most abundant energy source in the solar system, sunlight.
Solar pressure. Now, I know some listeners might hear solar sail and think of old sci-fi. Is the physics really solid here? How can light push something if photons don't have mass?
It's fundamental physics, actually. Photons, the particles of light, might have zero rest mass, but they definitely carry momentum. So when photons hit something, they transfer that momentum. If they get absorbed, they transfer some. But if they get reflected, which is what a shiny sail is designed to do, they transfer about twice the momentum, like bouncing a ball off a wall.
Ah, okay, so the sail is like a giant mirror.
Essentially, yes. A huge, incredibly thin, reflective membrane. It catches the momentum from countless photons hitting it.
But the push from a single photon must be minuscule.
Oh, absolutely tiny, infinitesimal. But the sun is always shining, so that tiny push is constant. It's there, 247 week after week, year after year.
And over time, that constant, gentle push adds up.
It adds up. It builds velocity gradually, slowly at first, but persistently. And the most beautiful part, it uses zero fuel once it's deployed. Zero.
That dream became reality thanks to Japan's space agency, JAXA, right?
Yes, with the Icaros probe. That was a fantastic mission back in 2010, a real game changer.
What did it do?
JAXA successfully deployed this square sail in space, controlled it, and used it to fly the probe all the way to Venus, powered only by sunlight.
Wow. Just pushed by light.
Just pushed by light. It proved the concept works in the real world, not just on paper or in computer models.
Okay, so proof of concept, check. But the review, it really digs into the challenges, the downsides. The engineering side sounds delicate.
Extremely delicate. Material science is the huge bottleneck here. For a solar sail to be effective, it needs to be incredibly light, but also incredibly large. We talk about aerial density, the mass per square meter.
You want that number to be tiny.
As low as possible. We're talking materials that are almost like smoke, gossamer thin, maybe just a few milligrams per square meter. But the sail itself needs to be vast, think multiple football fields in area.
So imagine trying to unfold something thinner than kitchen plastic wrap, but kilometers across in space without ripping it.
Exactly. And then you have to keep it tensioned, stable, pointed correctly. It's an engineer's nightmare.
What are these materials usually made of?
Specialized plastics, often polymers like CP1 or types of polyimide film coated with a thin layer of aluminum for reflectivity, but they also have to be incredibly tough.
Tough against what? Space is empty, right?
Not quite empty enough. They have to survive years, maybe decades, bathed in intense ultraviolet radiation from the sun, which degrades materials over time. Plus, there's constant bombardment by tiny dust particles, micrometeoroids.
Ah, space dust. Even a tiny speck hitting that thin film at high speed
Could potentially cause a tear, and enough small tears could affect the sail's structure, its tension, its ability to generate thrust efficiently.
Okay, so materials in deployment are hard.
Yeah.
But there's a more fundamental physics limitation too, right? Tied to distance.
Yes, and this is a big one. Sunlight, and therefore the radiation pressure it creates, follows the inverse square law.
Meaning the further you get from the sun, the weaker the push.
Dramatically weaker, the force drops off with the square of the distance. So if you go from Earth's distance, 1 astronomical unit, or AU, out to Jupiter, which is about 5 AU away,
The force isn't 5 times weaker, it's...
25 times weaker, 5 squared.
Ouch! That's a massive drop in acceleration.
It really is. It makes solar sails potentially great for missions inside the orbit of Mars, maybe out to the asteroid belt. But for deep space, going out past Jupiter to Saturn, Uranus, Neptune, or beyond,
The push becomes almost nothing.
pretty much negligible. Your acceleration just fades away. So for exploring the outer solar system or heading towards the stars, solar sails alone probably aren't the answer.
Okay, so if sunlight pressure gets too weak out there, what else is constantly flowing outwards from the sun that we could potentially push against?
That leads us to the solar wind.
Ah, not light pressure, but actual particles.
Exactly. The solar wind is this continuous supersonic stream of charged particles, plasma, mostly protons and electrons that flows out from the sun all the time. And crucially, it carries significant momentum and keeps a decent density much further out than where sunlight pressure becomes weak.
Okay, so if we can push against that, maybe we can get thrust further out.
Yeah.
This brings us to magnetic sails. Mag sails.
Correct. Magnetic sails. It's a totally different concept from reflecting light.
Because there's no physical sail, right? You can't reflect charged particles with a sheet of plastic.
Right. Instead of a physical membrane, a mag sail uses loops of superconducting wire to generate a really powerful, large magnetic field, an artificial magnetosphere, essentially.
Like Earth's magnetic field, but generated by the spacecraft.
Sort of, yes. And when the charged particles of the solar wind hit this magnetic field,
They get deflected, like how Earth's field deflects the solar wind.
exactly, the magnetic field pushes the plasma particles aside. And by Newton's third law, again, pushing the solar wind plasma away pushes the spacecraft forward. You're essentially sailing on the solar wind using a magnetic bubble.
That sounds incredibly cool. And it avoids the whole problem of deploying and maintaining huge, fragile sheets of material.
That's a major theoretical advantage, yes. No worries about UV degradation or micrometeoroid tears on a physical sail.
And because the solar wind doesn't drop off as quickly as light pressure.
The potential acceleration profile, especially in the outer solar system, could be much better than a solar sail. Better performance, potentially more durable.
Okay, sounds great. What's the catch? The review mentioned a massive technological chasm.
Ah, yes. The catch is, well, it's the scale. The sheer mind-boggling scale required.
How big are we talking?
To generate a magnetic field strong enough and large enough to effectively interact with the relatively low-density solar wind, especially far from the sun, you need enormous superconducting coils.
Define enormous.
The review, pulling from technical studies, suggests these superconducting loops might need to be, get ready for this, up to 50 kilometers in radius.
Oh, wait, kilometers, 50 radius.
50-kilometer radius, meaning the whole structure, the magnetic field generator, would be 100 kilometers across once deployed.
100 kilometers. That's bigger than any structure we've ever put in space by orders of magnitude. That's not a spacecraft. That's an orbiting installation.
We're hitting on the core problem. The scale is just immense, and that's only part one of the challenge.
There's more.
To get that magnetic field strength efficiently, the coils need to be superconducting.
Meaning they have zero electrical resistance. But that only happens when they're incredibly cold.
Exactly. Cryogenic temperatures. We're talking temperatures close to absolute zero.
So you have this 100-kilometer wide structure made of superconducting wire that needs to be kept freezing cold in space where sunlight is still hitting it.
Yes. You need a massive, complex, and incredibly reliable cryogenic cooling system, cryocoolers, running constantly for potentially decades.
The power requirements alone for that cooling system must be huge, not to mention just building, launching, and deploying a 100-kilometer structure.
Precisely. And the superconducting wire itself. It needs to be structurally strong enough to handle the immense magnetic forces trying to tear the coil apart while staying superconducting while being lightweight. We'd need breakthroughs in material science just for the wire.
So the technology to build the structure, deploy it, power the cooling, maintain those temperatures reliably for years.
It simply doesn't exist yet, not even close. We're researching things like high-temperature superconductors, or HTS, which could operate at slightly warmer, though still very cold temperatures, reducing the cooling load a bit.
But still needing significant cooling.
Oh, absolutely. Compared to the ambient temperature of space, even HTS needs serious refrigeration. The power generation, the thermal management, the deployment mechanisms for something that size, it puts MagSails firmly in the far future breakthrough category for now.
It's an incredible concept, but the engineering hurdles are just astronomical.
Yeah.
Okay, so if the MagSail is potentially too big, too heavy, too complex with the cryogenics, is there a lighter way to push against that solar wind?
Well, that's the thinking behind the next concept, electric sails or e-sails.
Electric, not magnetic. How does that work?
E-sails try to achieve a similar goal using the solar wind, but with a different physical principle and hopefully a much lighter structure. Instead of a magnetic field, they use electric fields.
Okay, how do you make an electric field push things in space?
The idea is to deploy a number of very long, very thin conductive wires, or tethers, radially outwards from the spacecraft, maybe spun out using centrifugal force.
Kilometers long, these wire?
Potentially tens of kilometers long, yes, but very lightweight. Then you use an electron gun on board the spacecraft.
An electron gun. What for?
To shoot electrons away from the spacecraft and the tethers, leaving the tethers with a strong positive electric charge. Maybe thousands of volts positive.
Ah, I see where this is going. The solar wind is mostly positively charged protons.
Exactly, like charges repel. So the positively charged tethers create an electric field around them that repels the incoming positive protons of the solar wind.
So you're pushing the solar wind away using electrostatics, not magnetism.
Precisely. And again, Newton's third law means pushing the wind away pushes the sail forward, away from the sun.
And the big advantage here is replacing those massive cryogenic superconducting coils.
With just long, thin wires and an electron gun. Potentially a much, much lighter system than a MagSail. That's the main appeal, escaping some of that enormous mass and complexity.
Sounds like a definite improvement in terms of mass. But the review probably points out new challenges too. No free lunch.
No free lunch in space propulsion, unfortunately.
Yeah.
E-sails swap one set of problems for another. The review highlights issues with, again, materials and also power.
Let's start with the materials. Kilometers of thin wires floating in space. Sounds fragile.
They would be. Very thin to save mass, very long to create a large enough repulsive area. That makes them incredibly vulnerable too.
Micrometeoroids again. Space dust.
Yep. A single hit probably wouldn't be catastrophic. The designs often involve multiple tethers for redundancy. But cumulative damage over years from tiny impacts could degrade the tethers, potentially sever them, or cause oscillations that make navigation tricky. Maintaining the integrity of potentially hundreds of kilometers of deployed wire over decades is a huge challenge.
Okay, so durability is one issue. What about power? You mentioned an electron gun.
Right. If MagSails need power for cryogenic cooling, E-sails need continuous, significant electrical power to run that electron gun.
Why continuously? Don't you just charge the wires once?
If only it were that simple. Space isn't a perfect vacuum. There's plasma everywhere. The electrons in the surrounding solar wind plasma are attracted to the positive tethers and will try to neutralize their charge. It's called plasma screening.
So you're constantly fighting to keep the wires charged up.
Exactly. You need to keep pumping electrons off the wires with the electron gun to maintain that high positive potential against the surrounding plasma. That requires a pretty beefy power source, multi-kilowatt level, running constantly, efficiently, and reliably for the entire mission duration, potentially decades.
So you trade the MagSails challenge of huge scale and cryocooling for the E-sails challenge of extreme wire fragility and continuous high power generation.
That's a good summary of the trade-off, yes. Still requires advanced materials, reliable long-term power systems. Significant hurdles remain.
Okay, wow. We've covered quite a range here, from the tried and true gravity assist to light sails, to these more exotic magnetic and electric concepts pushing against the solar wind. Let's try and bring it all together. What's the synthesis here? What does the review conclude when looking at all these options?
Well, when you lay them all out, gravity assist, solar sail, mag sail, e-sail, you see this clear spectrum. On one end, you have gravity assists, proven, working now, but totally inflexible. On the other end, you have mag sails and e-sails, potentially much higher performance, especially for deep space, but requiring technology that is, frankly, way beyond our current capabilities. Solar sails are somewhere in the middle.
Let's quickly recap the killer limitation for each, based on the review.
Okay. Gravity assists work great, but you're tied to rare planetary alignments, no flexibility, no autonomy.
Solar sails. Proven concept, steady thrust near the sun, but the materials are incredibly delicate, and the thrust just dies off way too fast with distance because of the inverse square law. Useless for the outer solar system or beyond.
Right. Then mag sails. Great potential performance, avoids material degradation, pushes against the solar wind further out, but the showstopper is the scale, those 50-kilometer radius superconducting coils needing constant cryogenic cooling. Just not feasible today.
And e-sails, lighter than mag sails, also uses the solar wind. But you trade the massive coils for potentially fragile kilometers-long tethers and the need for continuous high-power electron guns to keep them charged. Still big tech hurdles.
Exactly. So the big conclusion from the review, looking across all of this.
What does it all mean for actually getting out there?
It means there's no silver bullet. No single propellantless method solves all the problems right now. Each one has a critical flaw, whether it's flexibility, fragility, distance limits, or just requiring currently non-existent technology.
So the path forward probably isn't picking just one winner.
Very unlikely. The review strongly suggests the future probably lies in combining these approaches. Maybe use a powerful launch stage, then a solar sail to get good initial acceleration out of the inner solar system.
And then maybe deploy an e-sail or mag sail once a solar cell becomes ineffective to continue accelerating using the solar wind.
Something like that. Or using gravity assists strategically in combination with continuous low-thrust propulsion. Hybrid approaches seem much more plausible than relying on a single magic solution.
And that idea, needing these advanced propellantless methods, perhaps in combination, becomes absolutely critical when we talk about the really big goals, doesn't it?
Yeah.
Like interstellar travel.
It's non-negotiable for interstellar, really. The review hammers this home. If you're serious about reaching another star system within a human lifetime, or even a couple of centuries, chemical rockets just won't cut it because of that Tsiolkovsky mass ratio limit.
You simply can't carry enough fuel.
You can't. So leaving the propellant behind isn't just a nice-to-have for interstellar missions. It's probably the only way it could ever be feasible. It fundamentally changes the challenge.
From a challenge of energy storage, fuel, to a challenge of energy harvesting, light, wind, gravity.
Perfectly put. It becomes about building incredibly efficient, large-scale energy harvesting structures that can operate reliably for centuries.
Which suddenly makes those huge engineering hurdles. The 50-kilometer coils, the super durable tethers, the decades-long power sources seem less like science fiction pipe dreams.
And more like the necessary entry ticket. They define the scale of engineering required if we actually want to become an interstellar species. It's less about building slightly better rockets and more about inventing fundamentally new ways to build and power things in space.
This has been a really fascinating journey, breaking free, conceptually at least, from the tyranny of the rocket equation. We've looked at gravity assists, solar sails, magnetic sails, electric sails, each with its promise and its major roadblocks: flexibility, materials, scale, power.
And maybe, as we wrap up, it's worth focusing on that biggest technological gap. The mag sail scale, for instance. If we accept that something like a 50-kilometer superconducting structure kept near absolute zero for decades might be what it takes for truly fast deep space or interstellar travel. It poses a really interesting question for you, the listener, to think about.
Go on.
What kind of fundamental science needs to be discovered first? Before we can even think about designing the propulsion system, what breakthrough in, say, material science, maybe practical room temperature superconductors, or in compact ultra-long life power generation, maybe fusion power plants small enough for spacecraft? What needs to happen in the lab before the engineers can even start drawing up the blueprints for these propulsion systems?
That's a great point. We might not just be waiting for better engineering. We might be waiting for a whole new piece of physics or material science to unlock the path forward, the invention that enables the invention.
Exactly. The next leap in propulsion might start not in a rocket factory, but maybe with a discovery in condensed matter physics or advanced energy research. It really shifts your perspective on where the bottleneck lies.
A powerful thought indeed. We need the science before we can build the sails to truly navigate the void. Thank you for joining us on this deep dive into leaving the fuel behind.